Hi, I'm Sam Armstead,
I'm Alec.
And I'm Paul DiFrancesca.
and we are Battlefrog Physics. So for the second design process, we created 3 concepts for each of the 3 stations. We analyzed the pros and cons of each concept in order to decide which one to pick. We also researched older patents in order to not infringe upon those patents. We updated our Gantt chart, and we constructed an economic analysis model for our final product.
This is our Gantt chart. We have some slight modifications from our original Gantt chart. Our original Gantt chart had all 11 of our tasks in sequential order, with the one task being a predecessor of another. We've changed that. Now we have 2 sets of tasks that are in parallel with each other. The first set is concept testing and product architecture, which are shown right here. And then we have economic analysis and prototyping, which are down here at the bottom. We're currently in the middle of design for manufacturing phase, which is represented by a solid green line in our Gantt chart. The reason to change the original Gantt chart is because we needed more time for more important tasks like identification of customer needs, target specifications, because those are the underlying tasks that build the foundation for the rest of the task. Because you need to identify customer needs, that way you know there's a need for the product, and you need to target what the customer wants. Here we have our design structure matrix, or DSM for short. DSM serves a similar purpose to the Gantt chart, but the DSM does not show overall lengths or kind of give you a general idea of the overall project. The design structure matrix shows only task dependencies. So this X right here shows that task 2 is dependent upon task 1, task 4 is dependent upon task 3. These 2 tasks are in parallel with each other. That's why the X's are placed vertically. And similarly, in this fashion, the X's are placed vertically due to a parallel task.
Okay, so here we have the intellectual property. Essentially, from this chart, the only thing that's really relevant for our product is the screw-driven elevator. That's because we are actually going to use that to replace our current design, which is a conveyor belt-driven elevator. We ran into some problems with that, and it's overall just simpler to incorporate this rather than try to find some sort of solution. We'll have no problem using this design because the patent has expired. It's been expired for about 40 years. Next, we have the zipline trolley and the catapult device for use in an amusement game. Both of these, we will be using the general idea, but these exact designs are far too complex and large for our uses. So we will be designing more simple, smaller designs, and we shouldn't run into any patent problems or anything along those lines. Next, for the last 2, we have the funnel and the basketball backboard. For use in our BRG, basically we will be using the general geometric shape of these. However, we will not be using the exact ones themselves. For a basketball backboard, we're really just going to use a rectangle that will be acting kind of like a miniature backboard, but not near as large, made of the same material. As for the funnel, that patent has been expired again for that one, I believe 50 years actually. So we're good with that. Next, we have the concept generation and selection. So for here, we can see we have station 1. We have all 3 of our concepts. 2 of which are both conveyor belt based Arduino driven elevators, and one of them is a ramp domino effect station. We decided that we were going to go with the middle station for the station 1. However, as I said before, we're actually going to get rid of all this and use the screw driven elevator because we are still running into problems with the conveyor belt elevator design. Next, for station 2, we have basically a bounce plate design in which the ball rolls off the track, hits a plate, and comes back up onto another track. 2 plates, so it does it twice. We then have a catapult, and then we have a track through which the ball would roll and fall through a hole, come out the bottom. For this, we decided we were going to actually create a hybrid station between these 2 right here, replacing one of the plates with a catapult. It just goes for a more interesting design. As for station 3, again, we have, just like station 1, we have two very similar designs. We have the 2 zip line designs, and we have another catapult design. This one's spring-based, slightly different from the one in station 2. The reason we will be going with the middle station for station 3 is because these platforms over here provide stability for the ball as it enters and exits the zip line, overall reducing the odds that it will fall off the track or something will go wrong with the machine. Finally, we have the failure modes and effects analysis. So here, we basically incurred the same problems and the same failures between all the stations and station connections. None of them had too much to do with the design themselves. As you can see, we had a problem with manufacturing deformities, high ball velocity, product misassembly, and the Arduino code failure. The only one that was actually specific to one station was the Arduino code failure with the station 1 with the elevator. That would be if the customer were to put in a wrong code and it didn't compile or it ran the motor wrong, the elevator just wouldn't work or might work backwards or do some weird stuff we don't want to have. So going back to manufacturing deformities, that is the only problem coming from our side. Basically, if we use poor materials in manufacturing or any incidents where there's a broken piece comes out or a misshapen piece, that'll result in an overall failure because it won't line up with the measurements and the ball odds are it's going to fall off. Next, we have high ball velocity. Essentially, that one was if sometimes the ball will run too fast along the track. It doesn't happen too often, but it does happen sometimes. And it'll go so fast it just flies off the track. Third, we have the product misassembly. That is with regards to the customer. If the customer does not properly read the directions or confuses certain parts with other ones, and the whole piece just doesn't hold together, it could fall apart or things don't line up properly. That's one of the failures of the machine coming from the customer side. So out of all these, none of them occurred enough to actually warrant any change in the design or change in general process of the machine. However, we did come up with some solutions to try to reduce them. So we have more detailed instruction manual and supplementary video instructions. Those two go hand in hand with trying to reduce issues coming from the customer side, such as the Arduino code failure and product misassembly. Our third solution was the extreme inspection of parts before shipping. Basically, we want to thoroughly check over every single part, every single piece to make sure there are no deformities, there are no misshapen parts or anything like that, so that when it gets to the customer, it's all ready to be built.
Okay, so for the first station, we chose the second concept model of the elevator with the conveyor belt. And for design for manufacturing, we decided to 3D print the belt and hook system, as that requires a lot of precision and accuracy. That would be much better to use with a 3D printer. We also, the 3D printer can print parts already assembled for us, opposed to us assembling them after, and that would be very advantageous for us to take advantage of with parts such as the drive chain and other miscellaneous parts that go together. So for the second station, we chose the bouncer option mixed with the catapult, and for this we decided to 3D print the tracks, the supports, and the bounce pads all separately, and then assemble them ourselves after the printing. This will cut down on the large amount of support material that it will take to fill these large gaps right here, and thus save us money in the long term. We will also use a 3D printer because each track has a slight downward slope. That would be easier to 3D print opposed to making that ourselves. And the hard plastic bounce pads that the printer will print will provide a more efficient bounce for the ball. Lastly, the third station, we chose the second concept model for the zip line. And for this one, we'll 3D print the cable and trolley system. And for the cable, it will be a more rigid, not really a cable, more of a just angled support. And that will provide for more controlled descent. And for the trolley, to 3D print the trolley, it will connect better to the previously printed track of the previous station.
Here we have economic analysis. Here we have our cash flow diagram. We have initially a $10,000 investment from VTEPs. Then we have a $4,550 revenue for each quarter. Our cash flow diagram is broken down by quarters, 12 quarters, 3 years overall. We have an $800 manufacturing and operation cost per quarter, and then we have a $10,000 overhead cost at each year. So we have one for quarter number 4, quarter number 8, and quarter number 12. We're paying a 15% APR on the investor's initial investment into our program, which is $1,500 at the end of every year, and that nets $166.67 profit for us at the end of year 1, year 2, and year 3. And the entire debt will be paid back at the end of year 3, and then the rest will be profit. Here we have our conclusion. We've analyzed possible patents for each station to make sure we're not in intellectual property violation in any way, shape, or form. We created designs for each station and compared them and saw how we would be doing economically speaking with all of our printed parts and whatnot. We predicted how each station would possibly fail and address solutions. We evaluated our design, and then we analyzed that we would have a profit after 3 years.
Okay, we're at